Actually, this talk is organized as a dry run for a job talk interview, a job talk. So, yes, so please enjoy. Well, good afternoon, everyone. I'm here very excited to have this opportunity to present some of my contributions to the cloud and big data research. And we have some very exciting results to show. And my talk today, the title is Finding Needles in Cloud and Big Data Stack. Nowadays, we are living in a world and the internet connects almost every aspect of our life. Here are some of the typical web applications that we are using every day. In recent years, the word cloud has become more and more popular. As nowadays, these web services are running inside a cloud. So actually, inside the cloud, there are multiple general purpose machines, and they provide virtualized services towards the users or the customers. For example, in the cloud, it is usual that different machines are used to provide different sort of services. For example, we may use some machines to run deep learning applications, and we may use some machines to run Spark, that is a big data application. And we may also use some machines as a storage system. And these virtualized services, this approach is called virtualization. There is another trend in the cloud networking is that there are some major players or major companies in this area. They provide the cloud infrastructure to the public. So this is called infrastructure as a service. With this, smaller organizations or individual users will also be able to use the cloud to host their services. Nowadays, we are living in this particular world where every service is practically hosted in the cloud. So in the cloud, there are social network services like media and gaming services, and of course maybe bioinformatics and biomedical applications running in the cloud. As users, we are accessing these services every day. Whenever a user tries to access a piece of data in the cloud, the first step is always try to locate the data or the services. This is to say that the infrastructure of the cloud needs to answer this particular question. Where should I send the request to? Or we summarize this as we need to find a specific data object in the cloud. And this is a very critical task in cloud and big data. So in the past few years, I have been working around the cloud and network system area and the big data area. The cloud system provides the storage, process, and deliver of the big data. And those big data applications also yields new requirements of the infrastructure of the cloud system. So my research has been focusing on these three aspects of cloud and big data. That is the scalability of the system, the reliability of the system, and conduct more research about the applications in the cloud. So for the scalability issue, I have been working on these two projects. We have been working on the name and address lookups and the network architecture. For the reliability issue, we have developed a load balancer, and we also worked on monitoring and verification and failure recovery for the networks. As for the application side, I have been working on some applications in the bioinformatics area. I have been trying to build some applications for bioinformatics in the cloud. To be specific, I worked on these two projects, that is taxonomy classification and sequence storage and query. So out of these projects, 4 of them are built around an algorithm algorithm called Othello Hashing. So this is what I would like to share with you today. So Othello Hashing is the primary contribution of my dissertation. So I designed this algorithm, and we built some fundamental applications and tools for data and address lookups in cloud, network, and big data, or large databases for bioinformatics information. So next, I would like to share some of the outcomes of the Othello hashing. The main functionality of this Othello hashing is to provide key value lookup. So given a key, the Othello hashing will return a value. Here the keys can be any names or addresses or identifiers. And the value can be any meaningful fixed length integer value. And for the, we require that the length of the value are smaller than 64 for a better performance. So for example, in the network packet switching, this sort of application, the key is the network address, and the value is the outbound link of the switch. That is to say, when the switch in the network gets a packet, it will extract the data field in the packet and does a query. The query result will tell the switch where to send this packet. Another example is in taxonomy classification. And here, the key is a Kaymer, which is a substring of the item sequence. And the query result tells us a taxon. So that means what species does this sequence come from? So let me introduce some unique properties of Othello hashing. So Othello hashing is able to provide key-value lookups with very small memory and ultra-fast speed. So the first property, it is super fast. It only requires two memory reads operations during the query. So the querying speed is really fast. And also, the memory space, the memory requirement of Othello is really small. It only has like 10% to 30% memory requirements compared to some of the very famous hash tables. So here, compared to cuckoo hashing. So cuckoo hashing is actually a very advanced hashing table that is widely used in some of the cloud and big data applications. For example, Google TensorFlow used cuckoo hashing as their hash table. So this data structure, or this hashing method, was based on the theoretical results from the minimum perfect hashing. However, the theory results does not guide us how to provide an effective dynamic update for the minimum perfect hashing. So our contribution is to enable the dynamic updates in minimum perfect hashing. So Othello is able to support updates with over 1 million times per second. And this is very essential for the cloud and big data applications, because in the cloud, usually the keys and the values are changing. So we need to update the structure in a very fast fashion. So we see that we have the applications we build with Othello hashing, and these applications always achieve very fast speed and using very small memory cost. And this is very important for cloud and networking cloud and networking applications, because like faster memories such as TCAM is very power hungry and expensive on the devices. And those applications in the cloud usually have some real-time performance requirements for the speed of the query process. So using Othello, we tackle those problems of the cost and the real-time performance requirements. So I will use an example of name switching to demonstrate how Othello hashing works. So in computer networks, a switch is responsible to forward packets. On each of the switch, there is a data structure called forwarding information base. So, or we say FIB for short. So A FIB is actually a data structure, and it is usually a table. It is used by the switch to decide where to forward a packet. So when the switch gets a packet, it extracts the destination field from the packet and does a query over the FIB. And the query result will tell the switch where to forward the packet to. Obviously, the output of the FIB query is the forwarding action. So essentially, the FIB is a key to value mapping, and it performs key value lookup. We observe that, like in cloud networks, there is a trend of using names such as MAC addresses. This is for switches. And for LTE or 4G networks, they use the TEID as the names of the devices. And for the media services, we use data ID for the identifier for the contents. And for IoT, the devices also have a unique device ID. These sort of names are not aggregatable, which like IP address do. What that means in computer network is that a switch in the cloud, in order to maintain the FIB for all of those devices in the network, it has to keep the memory of all of the names of all of the devices of the network. So essentially, we will have a very long FIB. So when the FIB is too long and cannot fit inside the hash map faster memory of the device, it will boom just boom. So we say this is called FIB explosion, like when the FIB is too large to fit inside the switch. And this is the problem the cloud and network service has to face when the number of devices grow. So we indeed need some better approaches to represent the FIB. So our solution is to use Othello. So next I will introduce how Othello works. The very basic version of Othello focuses on this task. That is to classify keys into two sets, X and Y. So this is equivalent to a key-to-value lookup, where the value is just one bit of value. So the query result is denoted by TOK. TOK equals to 0 denotes that this k belongs to the first set X. If TOK equals to 1, that means the k belongs to the second set Y. And later we can extend this hashing mechanism to its advanced version, which is able to classify keys to 2 to the power of L sets. And that is equivalent to a k-value lookup for L bit values. So to compute the TOK value, the Othello hashing query structure maintains two bitmaps, A and B. The total size of the bitmap is smaller than 4n, where this n is the number of keys stored in this hashing. So in the bitmap, the values are assigned, the values 0 and 1 are assigned to the cells in the bitmap. So Othello also maintains two hash functions, HA and HB. For a query, for example here, the Othello query structure gets a key, which is here denoted by a purple square. It computes two of these two hash values and use them as the index on the bitmaps. And then it gets the values stored in the corresponding bits in the bitmap, and then compute a exclusive OR of these two values. So here, tall purple square equals to 1, then that is equivalent to say this purple square is in set Y. So the problem is, so as long as we have those values assigned into those bitmaps, then we can then just computing the tall value is really easy. So the question is, how can we assign the values into the bitmaps? How to construct this data structure? So the underlying mechanism of Othello is as follows. Othello actually maintains a acyclic bipartite graph. The vertices in the graph are denoted by U blah blah and V blah blah, which represents the corresponding indexes in area A and B. So each of the edge in the graph indicates a key in the set. So for example, here the purple square disk key, the hash values are 6 and 5, so there is an edge connecting U6 and V5. So similarly, for all of those other keys, we can connect those nodes in the graph. So the connection of this graph is decided by the hash function, and we require that this graph to be acyclic. So if during the process of adding the edges into this graph, if we meet a circle, then we can just pick another pair of hash functions until we find a pair of functions that generates a acyclic graph. So we prove that for an Othello, we can always expect to find a acyclic graph with expected 1.4 times, which gives us the time complexity of building the graph G is on average on linear time. So when we have the acyclic graph G, then we can assign the values in the bitmap. So here, the tall value of the purple key should be 1. Then we assign just one of its edge, one of it is and to be 1 and the other to be 0. We color this nodes in the graph as black and white. Then, as long as we follow the DFS order of the edge in the graph, if G is acyclic, it is really trivial to find the coloring plan of the graph and to find a assignment of the values in the two bitmaps. So, by the way, this is actually why we use the name Othello to this data structure, because during the construction or the update, the values in the bitmaps will flip from 0 to 1, and otherwise. So it is the same as Othello game. So next we extend the Othello to support classifications into 2 to the power of L sets. For example, we have 4 sets here, Z0 to Z3. We can easily separate the elements in the union set of these 4 sets into 2 sets, X1 and Y1. And we can also find another way to separate them into X2 and Y2. Using these orthogonal separations, we can use just L different Othellos to classify the names into 2 to the power of L sets. L Othellos can classify names to 2 to the power of L sets. So, following the method to split the elements in the sets, we are able to construct 2 Othellos. One is to classify keys in X1 and Y1, then the other is to classify keys in X2 and Y2. So one interesting property of Othello is that the graph G is decided by the union set of X and Y and the hash functions. So actually these 2 Othellos, the graph are actually the same. The only difference is their coloring plan, or we see the difference lies in the values inside the bitmap. So if we would like to conduct a query over those L Othellos in the same time, we would like to ask, do we need 2 L memory access trees to query over the L Othellos? The answer is no. The solution is to align the bitmaps together. So instead of bitmaps A1, A2, B1, B2, we now have arrays, big A and big B. each of the value is an L-bit integer. For example, A0 is the first element into Bitmap in A8. So for a query, we can directly get the L-bit values together. And we can do the arithmetic operations for L bits together. We know that the CPUs can read L bits at one time, as long as L is smaller than the word length. So the time complexity of conducting a query of all those L Othellos is actually exactly the same as if there is just one Othello. So the next we'll introduce how to use Othello to build the fib in the network switches. So essentially, the fib is a key-to-value lookup structure, where the key is the name and the value is the 14 actions. So as a data structure, the fib supports operations such as construct, update, and the lookup. The main idea of using Othello is consider we have a controller program that is running in the network. So this control program does not run on the switch, but it is running somewhere else inside the network. And the controller is more powerful than the switch, and the resource on the controller is more like abundant. So we can move the relatively complex structures that supports the construct and update towards the controller. When there is some like network dynamics happens in the network, we can ask the controller will ask the switch to update the lookup components, like using existing APIs of the programmable networks. And on the switch side, the lookup components are optimized for memory and query cost. The reason we can do this is because in the Othello, the bitmaps are the only components that are necessary to conduct a query. The graph is not necessary during a query. So we move the graph to the controller and we just left the two bitmaps on the switch. So next we show some comparison results with concise fib. This is to say we compare this with some existing works that is from Buffalo from Princeton and Othello Hashing from CMU and Intel. We measure the memory space on some of the typical fibs, and the memory size of concise, which is the name for Othello in fib, is much smaller than that of Cuckoo and Buffalo. And so usually it is only about 10% to 30% of that of Cuckoo. This figure shows the query speed of the concise fib. This shows the speed of the four of the different FIB designs. So the x-axis is the number of names, and the y-axis is the query throughput. And we see that concise is able to demonstrate about 2 times to 4 times speed advantage than the other solutions, and it is even able to support almost 5 million queries per second. But with this, the data in this figure was measured on a journal-purpose desktop computer, so we can see that the performance of Othello in fib is very high. So next, I will just show some other project that we built with Othello. So we built a load balancer with Othello. Let's first see what is a load balancer. So suppose a user opens a browser and would like to see some videos. In this case, Gangnam Style. So a URL that carries the ID of this video will be sent to a gateway server of YouTube. And that server will forward the request to one of the backend servers that hosts that piece of data. So suppose there is another user who would like to access the same video. The gateway may choose to send that request to the same backend server or another backend server. So in this case, the gateway works as a load balancer. So the load balancer needs to distribute the request for the users among the servers. So we see that a load balancer is a really important fundamental functionality of the cloud service. And also, a load balancer needs to balance the load across the different servers. So we, using the Othello hashing, we built a layer 4 load balancer, and there are so we see that the existing solutions for those load balancers always face a dilemma. So that is to say, the load balancer either needs to store all the connections, or using the digest of the users. So these will either have high memory cost, or cause some false hits. So using Othello, we use the country, and it just represents all the current connections by only 2 areas and brings nearly neither false hit nor consistency violation. So in this project, Othello hashing serves as the key component that tracks the connection between the users and the backend servers. And Othello hashing also supports faster queries. And this work can be implemented on either commodity servers or programmable ASICs. So we compare this concurrent load balancer to some of the actual load balancers that is actually used by Google or Verified networks. We show that the concurrent is able to demonstrate much higher query speed without getting false hits. So the next part, I will introduce 2 of these applications that we built in Othello in the bioinformatics area. So using Othello, so nowadays, we are living in this world that is full of living things. So the central dogma of molecular biology tells us how this world works. So the genetic code in the DNA is transcribed into RNA and then into protein. So in order to understand the details of the genetic code, we need to know what information is encoded in the sequence. So in order to get such sequence, researchers have developed multiple generations of sequencing technologies. These sequencing machines gives us a sequence of TCGA characters that represents how the DNA or RNA sequence is arranged. For us, this sequence is just like a book of genetic code that we can use this book to understand how our life works. So this sort of RNA-seq data is the fundamental resource of all the biological or life science research. In the past decade, the sequencing technology has been evolving rapidly. The speed of the advancing of sequencing technology is way more beyond Moore's law. However, in the computer science, we are in the computer science area, we know that the system performance are still struggling to catch up with the Moore's law. That is to say, nowadays we have more sequencing data generated than we can process. Hence, there is a great need in the bioinformatics area, that is, how to effectively store the sequencing data and how to effectively conduct a global survey on such data. So the term global survey, I would like to expand this a little bit further. So let me use an example to show what is a global survey. So here we are talking about a global survey on the TCGA pan-cancer dataset, which is short for the Cancer Genomic Atlas. It is very large. It contains tens of kilos of samples of multiple types of cancers, and the raw data is really large, and it is almost 54 terabytes, and is ever growing. So in this database, there are multiple. In this database, there are samples, which is essentially the sequencing results from anonymized patients with different types of cancer. Suppose someone is able to get his own sequence result and conduct a compare between his own sequence result towards those results in the database. And if the comparison result indicates that the comparison result may indicate something happens with this red cancer type, then we can maybe able to know that this person may have also have this sort of disease, and then we can send this person to further diagnose or therapy if necessary. So early diagnosis of severe disease will indeed save life. You see, the survival rate is 5 to 10 times higher for early diagnosed disease than the late stage disease. But why we are not having this sort of global survey on the dataset in our annual body check? This is because nowadays the current approach is too slow. Nowadays, each of these comparison will take several hours, and in order to conduct a global survey, it will take several years. So it is not practical to conduct a global survey for personal sequencing data. So next, I will explain how to use Othello hashing to save human lives. So there are some current approaches that are able to conduct research on a smaller number of samples, but none of them are able to scale to the size of the TCGI dataset. For example, the metadata-based approach has to access a very large data set, has to process the very large amount of data. And the quantification approach is really computationally intensive, and it will take 2 years CPU times to analyze the result. Some recent approach called SVT is a little bit better. It is from CMU, but however, it is still not able to scale over 1,000 of samples, and it is relatively slow in performance. And more importantly, it is not able to generate a very detailed result of the comparison. So in our applications, we use the term Kaymer to represent the minimum unit of the sequencing. Remember that we say the genetic code is a book, and the sequencing technology is used to let us know the content of the book. So for a regular book, we are able to get small fractions or small pieces of text in this book. For example, this is called a sentence. The basic unit of text processing is called word. You all know that. We can always cut the sentence into small words and then count the frequency of the word in the book, and then we can get a word list. If we see a word list that says there is a book that primarily consists of words like algorithm, binary, computer, then we can say that this book is likely to be a computer science textbook. So this is similar to the sequencing data. Instead of book, we use instead of words, we use the term Kaymers as a very basic unit. Kaymer means a consecutive substring of length k. So for example, for this sequence, we set k equals to 5, and then we can get a lot of substrings of length 5 that are the Kaymers for this sequence. And similarly, we can get a Kaymer list of the sequencing data. And the Kaymer list is actually how the genetic data is represented in our database. The goal of conducting a global survey is comparable to a Google search. So when we type in a series of words in Google, Google will break the word or